our immune system is remarkable, really.
Oh, absolutely.
And it's got these, kind of ancient molecular guards that are found in so many different creatures. It's crazy.
It is, yeah.
Like flies, sea urchins, humans.
Yeah, it's wow.
And they're called toll-like receptors, TLRs. We're going to talk about those today.
Yes.
But how do these, they're like microscopic sentinels.
Right.
How do they tell the difference between, a good bacteria in our gut
Yeah,
and a really bad pathogen that could make us sick?
the big question, right?
Right, exactly.
How do they know?
And then how could we use that knowledge to, really help our patients with
Yeah.
diagnosing and treatment and everything?
Yeah, the clinical application of all this basic science.
Absolutely. So that's what we're going to talk about today.
Cool.
We've got two really interesting papers. Structural and functional understanding of the toll-like receptors.
Sounds dense.
It's from Protein Science. And then toll-like receptors and the control of immunity from Cell.
Very cool. So kind of from both sides.
Yeah, we're going to look at the structure and function and then, how they control immunity.
I like it.
So we want to make this clinically relevant for you guys, listeners.
Absolutely.
So healthcare providers and medical residents.
Yeah.
So you can use this information.
Practical takeaways.
Yeah, practical stuff, exactly.
Love it.
So let's just start at the beginning.
Okay.
What are TLRs?
All right. So TLRs, think of them as like the eyes and ears of our innate immune system.
Okay.
Our body's first line of defense, right?
Right.
So imagine them kind of like Border Patrol agents, right? They're just constantly scanning for anything that looks suspicious.
I like that.
Right.
Like at the airport.
Yeah.
Looking at people's passports.
Exactly. Yeah.
Checking for anything.
Yeah. But instead of passports, right?
Mm-hmm.
They're looking for these molecular patterns called PAMPs. Yeah. Pathogen-associated molecular patterns.
Okay.
So these PAMPs are like red flags
Okay.
that signal danger to the immune system.
Danger, got it.
Right.
Okay.
So they're specific molecules or structures.
Okay.
And they're found on bacteria, viruses, fungi, things that shouldn't be there.
Things that don't belong.
Right, exactly.
Yeah.
So they're the things that are like, uh-oh, this is bad.
So the TLRs are kind of like the security system
Yeah.
that's programmed to see those.
Recognize those threats.
Exactly.
Yeah.
Like a smoke detector that only goes off for smoke.
I love that. Yeah.
Burn toast.
Perfect analogy.
Yeah.
And just like you have different smoke detectors for different kinds of fires, right?
Wow.
We have different types of TLRs.
Okay.
And they're specialized to recognize specific threats.
Oh, interesting.
So humans, we've got 10 different ones, TLR 1 through 10.
Wow. Okay.
Yeah.
So it's like we've got a whole team.
A whole team of security guards.
Yes.
Sure.
Specialized.
Each one is trained to spot a different kind of intruder.
That's a great way to think about it.
Right.
Yeah. Okay.
So some TLRs, like TLR4, they're experts at detecting gram-negative bacteria because they can bind to lipopolysaccharide, or LPS.
LPS.
Yeah, which is a key component of their outer membrane.
Got it.
And then you've got others like TLR3, 7, and 8.
Okay.
They're really good at recognizing viral RNA.
Okay, so that's really helpful. But then if they're so good at detecting these foreign invaders,
Right.
how do they know not to attack our own cells?
Yeah. How do they avoid friendly fire?
Right. Wouldn't that be the security system?
Attacking the residents.
Yeah. That doesn't make any sense.
That's a great question.
Yeah.
And the papers we looked at, they actually go into a lot of detail about how our immune system is that smart.
Okay, so this is where it gets really clinically relevant.
This is where it matters, yeah.
Yeah, tell me more.
Okay, so one of the key mechanisms is compartmentalization. So TLRs that recognize nucleic acids, like TLR3, 7, and 8, they're actually kept inside these little compartments called endosomes.
Endosomes.
Yeah, think of them like secure vaults within the cell.
Okay.
So they don't accidentally bump into our own DNA or RNA.
Got it.
Right, because then that would be a problem.
Right, it'd set off the alarm.
Exactly. That would trigger an unwanted immune response.
Okay, that makes sense. So it's like keeping the really sensitive alarms.
Yeah.
Locked away.
Until you absolutely need them.
Unless it's really necessary.
Right.
And I imagine this is especially important with viruses.
Viruses are, yeah.
Because they get into our cells.
Right. They hijack our machinery.
Yeah.
And then they release their own nucleic acids.
Exactly.
It's like a Trojan horse.
It is.
Totally.
Okay, that makes a lot of sense.
And then another safeguard is this process called cleavage for activation.
Cleavage for activation.
Yeah, it's a mouthful.
Okay.
But some TLRs, like TLR9, which detects bacterial and viral DNA, it actually has to get chopped up a little bit inside those endosomes before it can even signal.
Really?
Yeah, so it's like an extra layer of security.
Wow.
Right.
Okay.
Making sure that the alarm only goes off when there's a real threat.
So it's like a safety on a gun.
Exactly, yeah.
You know, it's like an extra step to prevent accidental firing.
I love that. Yeah, it's perfect.
Okay.
And then to make sure that everything is running smoothly, there's the chaperone protein called UNC93B1.
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 Okay, I'm going to write that down.
Yeah, you probably will.
Okay.
But this guy, he acts like a guide, making sure that all the TLRs get to their correct locations and are ready to act when they're needed.
Like a crossing guard for TLRs.
Exactly. Yeah, they're like, all right, you go over here, you go over there.
You're needed in zone 3.
That's it. Yep.
Okay, so I'm starting to get a picture of how these TLRs work.
Cool.
And how our body makes sure they don't go rogue.
Yeah, it's pretty amazing, right?
It is.
It's really elegant.
Yeah, and this is where it gets really interesting clinically, right?
This is where it matters.
Because if the TLR signaling goes wrong, that can lead to all sorts of problems.
All sorts of diseases, yeah.
Yeah, like sepsis.
Sepsis, big one.
Autoimmune disorders.
Yep.
Even cancer.
Cancer, that's right.
So this is where, like, the rubber meets the road, right?
This is where the basic science translates into better care for patients.
Exactly.
Right.
So let's talk about that signaling cascade.
Okay, let's dive in.
Yeah.
So it all starts with the TLR binding to its specific PMP.
Right.
The red flag.
The red flag, it's like a lock and key, right?
Okay.
The PMP is the key that fits perfectly into the lock, which is the TLR.
Got it.
And then this binding causes the TLR to change its shape.
Interesting.
Right.
Okay.
And that process is called dimerization.
Dimerization.
Yeah, it's a fancy word, but basically it brings two TLRs together.
Okay, so they team up.
They team up.
Like the security guards. Exactly. They're like, oh, we both see it. This is bad news.
Okay.
And so then that dimerization, that triggers a whole cascade of signals within the cell.
Okay.
And these signals, they get transmitted through two main pathways.
Okay.
The MyD88 dependent pathway and the TREF dependent pathway.
Two pathways. Okay, so it's not just like one alarm bell?
No, it's much more complex than that.
Right.
Think of them as like two different alarm systems within the cell.
Okay.
Each one leading to a different immune response.
Different response depending on the type of threat.
Exactly.
Okay.
So the MyD88 dependent pathway.
The MyD88.
That's like the rapid response team.
Okay.
It triggers inflammation.
So like calling in the troops.
Yeah, like sending out the first responders.
Got it.
Right.
Okay.
And that's what causes, redness and swelling and pain at the site of infection.
Right, all those inflammatory molecules that we hear about.
Cytokines.
Yeah, like TNF-alpha, IL-6.
All those guys, yep. It's like setting off the fire alarm and calling the fire department.
Perfect analogy.
Right.
Okay.
Now, the TREF-dependent pathway, that's more like the Special Forces unit.
Ooh, okay.
Right. The elite team.
This one's specialized for fighting viruses.
Okay.
And it does that by inducing the production of interferons.
Interferons, those are the antiviral proteins.
You got it.
That help our cells, like, resist viral infection, right?
Exactly.
So it's like sending in a highly trained team to deal with a very specific problem.
That's a great way to think about it, yeah.
Okay, this is really helpful.
Good, I'm glad.
So it's not just one simple response.
Nope.
It's this really carefully orchestrated process.
It is, yeah.
And there are these different pathways that are tailored for specific threats.
It's beautifully designed.
It really is.
It's amazing.
So I can already see how this is going to be helpful in the clinic.
Right.
Yeah.
It all comes back to that.
And we're just getting started.
We're just getting started.
Okay. There's so much more to talk about.
I'm excited.
So to really get into the clinical relevance of TLRs, we need to look at how these pathways can go wrong.
Okay.
Because when they do, that's when we see all sorts of diseases pop up.
That makes sense.
Right.
Yeah.
So for example, let's talk about sepsis.
Sepsis. Yeah.
A life-threatening condition.
Huge problem clinically.
Huge, yeah.
We see it all the time.
All the time. And TLRs, they play a big role.
Okay.
In that inflammatory cascade that characterizes sepsis.
So in this case, it's not that the TLRs aren't working.
Right.
It's that they're like overreacting.
They're overreacting. It's like they're going haywire.
Yeah.
Right.
Okay.
Too much of a good thing.
Right.
Leading to this dangerous level of inflammation.
Like that cytokine storm that we saw with COVID.
Exactly. Yeah. Good connection.
Yeah.
So understanding TLRs in these situations is super important.
Yeah.
For developing better treatments.
So like we can't just target the infection. We have to target the immune system's response.
Exactly. It's about restoring balance.
Right. Balance. That's key.
Yeah. Bringing things back to equilibrium.
I like it.
So researchers are looking into things like TLR antagonists.
Antagonists.
Yeah, which can actually dampen that immune response.
Okay.
Kind of like turning down the volume.
Turning down the volume. I like that.
Right.
Okay.
Instead of just trying to, nuke the infection.
Right. It's more nuanced.
Exactly. Much more nuanced approach.
This is really fascinating.
I know. It's cool stuff.
I can see how this could really change how we approach things in the clinic.
Absolutely. And we're just scratching the surface.
I know. I can't wait to learn more.
There's a lot more to explore.
Okay, great.
But I think to really understand this, we need a good example.
Okay, yeah, let's do it.
Let's look at TLR4 and LPS.
Okay, LPS. That's that molecule we talked about earlier.
Exactly.
Okay, so LPS?
Lipopolysaccharide.
Lipopolysaccharide.
It's a major component of the outer membrane of gram-negative bacteria. So it's like a giant red flag that screams bacteria.
Bacteria, got it.
Right.
Okay.
And TLR4 is the guard that's trained to see that flag.
Right, okay.
Now here's the cool part.
Okay.
The interaction between LPS and TLR4, it's not just a one-step process.
Oh.
It's more like a relay race.
Okay, I like that analogy.
Right.
Yeah.
So LPS gets passed from one molecule to the next,
Okay.
amplifying the signal at each step.
So who are the runners in this race?
All right. So first up, we've got LBP, LPS binding protein.
LBP.
He grabs onto LPS in the bloodstream
Okay.
and delivers it to CD14.
CD14?
Yep, a protein found on immune cells like macrophages.
Got it.
So he's like the first runner grabbing the baton,
Okay.
racing off.
Okay.
Then CD14 passes the baton to MD2, another protein that hangs out with TLR4.
Okay, and then finally MD2 delivers it to our waiting TLR4.
You got it. That's the finish line.
Wow. And that's how even a little bit of LPS can trigger such a big response.
Exactly. It's amazing, right?
Yeah.
Like a single bacterium can alert thousands of macrophages.
Wow.
It's like a chain reaction.
That's incredible.
Leading to this massive recruitment of immune cells to fight the infection.
Okay, but bacteria aren't just going to let that happen.
Oh, of course not. They're smart.
Yeah.
They've evolved ways to disguise themselves.
Oh, sneaky.
Right.
Okay.
So some bacteria, they've actually modified their LPS.
Okay.
So they can evade detection by TLR4.
So they're like changing their uniform so the TLR4 guards don't recognize them.
Exactly. Yeah, it's like a constant arms race between host and pathogen, always adapting.
That's fascinating.
Isn't it?
Yeah, this whole LPS story
has
really helped me visualize how this whole intricate process works.
Good, I'm glad.
So I guess what I'm wondering now is, what about TLR-based therapies?
Good question.
What's the current state of the research?
Yeah, are we using them yet?
Are we there yet?
Almost. Researchers are exploring both TLR agonists and antagonists as potential therapies.
Okay, can you explain the difference between those?
Sure. So TLR agonists, think of those as like the boost button for the immune system.
Oh, right.
So they bind to TLRs and activate them, enhancing the immune response.
Okay.
So they're being investigated as vaccine adjuvants.
Vaccine adjuvants.
To help vaccines work better.
Okay.
And also for cancer immunotherapy.
Okay, so revving up the immune system to fight cancer.
Exactly, yeah, turning up the heat.
Got it.
And then TLR antagonists, those are like the mute button.
Okay, so they block the signal.
They block TLR signaling,
Got it.
dampening the immune response.
Okay.
So those are being studied for treating inflammatory and autoimmune diseases.
Okay.
Where the immune system's kind of overreacting.
Right, causing problems.
Exactly.
So it seems like there's huge potential for TLR-based therapies.
Oh, absolutely.
To really change how we treat a wide range of diseases.
I think so, yeah.
But I imagine there are also a lot of challenges.
Of course, there always are.
Yeah.
With anything new, especially when you're messing with the immune system.
Right.
You got to be careful.
Yeah.
So researchers are working really hard to figure out the right dosages, the right durations to make sure that it's effective, but also safe.
So it's like finding that sweet spot.
Finding that sweet spot, that's a great way to put it.
Yeah.
You want to stimulate the immune system enough, but not too much.
Not too much.
Right.
Yeah.
It's a delicate balance.
It is.
But the potential benefits are huge.
It sounds like it.
Really huge.
I'm excited to see where this goes.
Me too. It's an exciting field.
That really is.
Yeah, it's a balancing act for sure.
It is. It really is.
And that's why, understanding this stuff is so important for healthcare providers.
Totally. I mean, we've been talking about sepsis, SLE, cancer.
Yeah, big ones.
But how do we actually use this knowledge with patients?
Right. How do we take it from the lab to the bedside?
Exactly. What are the actionable steps?
So first off, just recognizing that TLRs are involved in all these diseases can help us diagnose them better.
Okay, so it's like another tool in our toolbox.
Exactly. It's another piece of the puzzle.
Right.
So if a patient comes in with certain symptoms and we're thinking, maybe TLRs are messed up here.
Okay.
That can guide our testing.
Right.
Lead to a more accurate diagnosis.
Okay, so like let's say we're thinking sepsis.
Sepsis, perfect example.
Okay.
Knowing their TLR profile could be really helpful.
That makes sense.
Right.
Yeah.
So it helps us get to the root of the problem.
Okay, and once we have a diagnosis,
then what?
How do TLRs help us treat the patient?
Well, let's stick with sepsis for a minute.
Okay.
We know that TLR2, 4, and 9, they're driving that inflammation.
Right, that cytokine storm.
Exactly. So researchers are looking at ways to target those TLRs with therapies.
To kind of calm things down.
Exactly, to dampen that overreaction.
Interesting. So are there any specific therapies being looked at for sepsis?
Oh, yeah. There are a bunch.
Right.
For example, TLR4 antagonists.
TLR4 antagonists.
Like Eritorrent.
Eritorrent, okay.
That's one that's shown some promise in clinical trials.
Right.
The idea is to block that excessive signaling from TLR4, which is usually triggered by LPS from gram-negative bacteria.
Right, that makes sense.
So by blocking TLR4, we can potentially reduce that inflammation.
And hopefully better outcomes for patients.
That's the goal.
Yeah, okay, that's really promising.
And this idea of modulating TLR activity, it applies to other conditions too.
Like what?
Autoimmune diseases.
Okay, like SLE.
SLE, perfect example, where TLR7 and 9 might be attacking the body's own tissues.
Right, so it's like friendly fire.
Exactly, the immune system's gone rogue.
Okay.
So in that case, we might use TLR antagonists.
To block those TLRs from doing more damage.
That's the idea, yeah.
Okay, so are there any TLR antagonists being used for SLE?
Yeah, actually there are.
Oh, really?
One called anifrolumab.
Anifrolumab.
It's a TLR79 antagonist.
Okay.
And it's been approved for treating moderate to severe SLE.
Wow, so this is really happening.
It is. The research is translating into real treatments.
That's amazing. It's so cool to see how understanding these mechanisms leads to these targeted therapies.
It's like having a new lens to view these diseases.
Exactly.
It opens up a whole new world of possibilities.
It really does.
And even in cancer, TLRs are emerging as potential targets.
Oh, wow.
Yeah, so in some cases, we might want to boost TLR signaling.
To enhance the immune response against the tumor.
Exactly, like giving the immune system a little extra firepower.
Okay.
But in other cases, we might want to dampen it.
To control inflammation.
Right, because sometimes inflammation can actually help the tumor grow.
Right, it's complicated.
It is, yeah. Cancer's a tricky beast.
It is.
But TLRs are definitely part of the equation.
So, are there any specific examples of how TLRs are being used in cancer treatment?
Yeah, so one exciting area is using TLR agonists as adjuvants for cancer vaccines.
Adjuvants, those are like the boosters.
Exactly. They help the vaccine work better.
Okay.
So the idea is to stimulate the immune system to make it more effective at targeting cancer cells.
Interesting.
Like, for example, imicamod.
Imicamod, okay.
It's a TLR7 agonist.
Okay.
And it's already used for some skin cancers.
Okay.
And researchers are looking at it for other types of cancer, too.
So it's like we're supercharging the immune system.
Exactly, yeah. We're giving it the tools it needs to fight back.
That's really cool.
It is. It's pretty amazing stuff.
But I imagine there are also risks involved with, like, manipulating the immune system.
Of course, there are always risks,
Yeah.
especially when you're dealing with something as powerful as the immune system.
Yeah.
So one of the biggest challenges is making sure that TLR modulation is targeted and controlled.
Right, so we don't trigger unintended consequences.
Yeah, exactly. We don't want to create more problems than we solve.
Right, so it's all about finding that balance again.
It always comes back to balance, doesn't it?
It seems like it.
Yeah, it's like a delicate dance.
Yeah.
But the potential is huge.
I agree.
If we can get it right.
It sounds like TLR research is going to be really important in the future.
Oh, absolutely.
Yeah.
I think it's going to revolutionize healthcare in the years to come.
I'm excited to see where it goes.
Me too. It's a fascinating field.
It is. It really is.
And that's why we encourage you all to stay curious, keep learning.
Absolutely.
The more you understand about TLRs, the better equipped you'll be to use this knowledge in your practice.
Well said. It really is exciting to see where it all goes.
Absolutely. And to think, you know, we started with toll receptors in fruit flies.
Yeah.
And now we're talking about these groundbreaking therapies for humans.
It's incredible how far we've come.
It really is a testament to scientific curiosity, you know?
Absolutely. And it all comes back to those questions we asked at the beginning.
Right, about why TLRs are so important across so many different species.
And how they know to attack the bad guys, but not our own cells.
Exactly. Those questions have been like a thread through our whole discussion.
They have, haven't they?
And the answers are important not just for, like, textbook knowledge,
right,
but for actually taking care of patients.
Absolutely. I mean, as healthcare providers, we're always trying to get better at what we do.
Of course.
And understanding TLRs, it's like a key piece of that puzzle.
I agree. It's like having a new set of glasses to see the immune system with.
Exactly.
So, we've covered a lot of ground today.
We have.
From the basics of TLRs to their role in all sorts of diseases.
Sepsis, autoimmune diseases, cancer, even the microbiome.
It's amazing how much these little receptors do.
It really is. So what's the big takeaway for our listeners?
I think the main thing to remember is that TLRs are more than just, like, some random part of the immune system.
Okay.
They're really important for health and disease.
Right. And understanding how they work can actually change how we treat patients.
I agree. So by understanding their role in these conditions and staying up to date on the new therapies,
exactly,
healthcare providers can make a real difference.
Absolutely. Better diagnoses, more targeted treatments, better outcomes for everyone.
That's what it's all about.
It is.
So, as we wrap up, what's your final call to action for everyone listening?
Keep learning.
Yes.
The world of TLRs is constantly changing.
It is.
There's always something new to discover.
Absolutely.
So stay curious, keep exploring, and who knows, maybe you'll be the one to make the next big breakthrough.
That's a great thought to end on.
Thanks.
It's been a pleasure talking about this with you.
Likewise, I always enjoy these conversations.
And to our listeners, you can find the disclaimer and a complete bibliography in the description of this episode.
All the sources we talked about today, including those 2 papers.
Structural and Functional Understanding of the Toll-like Receptors from Protein Science, and Toll-like Receptors and the Control of Immunity from Cell.
So until next time, keep exploring those frontiers of science.
And remember, knowledge is power.
Especially when it comes to health. Disclaimer and bibliography in the description.